In the unending silent dark between the galaxies, the cosmos plays out its dramas unseen. Across voids of unimaginable scale, time itself stretches and thins. Here, in this profound emptiness, great symphonies of creation and destruction unfold. They are written in a language of fire and gravity far beyond the reach of our senses. We drift on our pale blue world, largely oblivious to these titanic events. Our eyes, evolved for the gentle light of a single nearby star, are blind to the true fury of the universe. For millennia, we looked up and saw only a serene, unchanging celestial tapestry. But we have since forged new eyes for ourselves, instruments of exquisite sensitivity. These technological senses perceive the cosmos not in the gentle hues of visible light, but in the energetic shouts and whispers of the invisible spectrum. And out there in that invisible realm, phantoms stir. Flashes of immense power briefer than a heartbeat erupt and vanish without a trace. They are cosmic ghosts, leaving behind only a momentary shiver in the fabric of space-time. For decades, we knew these apparitions were there, catching fleeting glimpses by chance. Now, a new sentinel orbits our planet, its gaze wide, its purpose singular. It is the Einstein Probe, a hunter designed specifically to catch these ghosts in the act. Its mission is to stare into the abyss and wait for the briefest flicker of a hidden fire. On the 7th of November 2024, the abyss stared back. A stream of data encoded as sterile numbers flowed from the orbiting observatory. It traveled at the speed of light to a ground station, a silent messenger from the void. Deep within the circuits of a processing center, an algorithm sifted through the noise. It searched for a specific signature, a pattern indicating a sudden, violent release of X-rays. Suddenly, a flag was raised, a trigger, an anomaly. The machine, devoid of emotion, had witnessed a cataclysm. It assigned the event a simple, unpoetic name, EP241107a, the first transient phenomenon detected by the Einstein Probe on that specific day. Across the globe, pagers buzzed and computer terminals chimed. An alert stripped of all but the essential facts shot across the internet. Coordinates, time, intensity, a call to arms for the world's astronomers. A new phantom had appeared on the cosmic stage, and its performance was already over. The curtain had fallen. All that remained was a rapidly fading echo. The hunt had begun. The Einstein Probe that made this discovery is a marvel of celestial cartography. Unlike traditional X-ray telescopes, which peer at the sky through a narrow keyhole, this sentinel employs a revolutionary design inspired by a creature of the deep sea. It uses micropore optics, a technology aptly named the Lobster eye. Imagine the multifaceted eye of a crustacean, each tiny element a separate lens. Each one gathers light from a slightly different angle. Together they form a panoramic, all-encompassing view of the world. The Einstein Probe's wide-field X-ray telescope functions in a similar manner. Thousands of tiny square tubes coated with reflective iridium line its detectors. X-ray photons arriving from distant cosmic shores glance off the inner walls of these tubes. They are gently guided and focused onto a sensor, creating a vast image of the X-ray sky. This instrument doesn't hunt for specific targets. It watches everything at once. It is the ultimate cosmic surveillance camera waiting for the universe to show its hand. And EP241107a was a flash caught in its peripheral vision, a profound irregularity. The data showed a source that had materialized from nothing. It flared to an incredible brilliance in the high-energy X-ray spectrum, and then within minutes it had faded back into the black. To comprehend the challenge posed by such an ephemeral event, consider an analogy grounded in our own terrestrial experience. Picture yourself standing atop a mountain on a moonless, starless night. The world around you is a canvas of absolute black, an ocean of ink. You are watching a distant, opposing mountain range miles away across a dark valley. Suddenly, from one of those faraway peaks, a single brilliant camera flash erupts. For a fraction of a second, it illuminates a tiny patch of the landscape, then vanishes. Your eyes register the brief burst of light, but the darkness that follows is absolute. The photographer is gone. The moment is lost. Now the questions begin to flood your mind. Who was there? Why did they take a picture in the dead of night? What were they trying to capture? Was it the opening act of something larger, or the final fleeting signal of an event already concluded? You have only one clue: the direction from which the flash originated. This is the predicament of the astronomer hunting a fast X-ray transient. The initial detection by the Einstein Probe was that single, startling flash in the dark. EP241107a was the cosmic photograph taken by an unknown actor for an unknown reason. Now the scientific world had to race to that distant mountaintop. They needed to search for any lingering evidence: a footprint, a dropped lens cap, the faint warmth of a recently used battery. They had to do it before the cosmic winds erased every trace that anything had ever happened at all. The very brevity of the signal is what makes it so tantalizing. It speaks of processes that are incredibly compact and fantastically energetic. Longer events, like the brilliant death of a massive star in a supernova, can glow for weeks or months, their light curve telling a detailed story of the explosion. But a fast X-ray transient, an FXT, is a whisper. It implies an engine of immense power that can switch on and off almost instantaneously. This points not to the stately death of a giant sun, but to something far stranger. It points to the realm of degenerate matter, to the bizarre physics of stellar corpses. This hunt for the universe's most fleeting explosions is a very recent chapter in our cosmic story. For most of human history, the heavens were a clockwork of reassuring permanence. Only in the 20th century did we begin to understand the true violence simmering beneath that placid facade. Our journey into the high-energy universe began not in a grand observatory, but strapped to the top of captured V-2 rockets after the Second World War. Physicist Riccardo Giacconi and his team, pioneers in a field that did not yet exist, placed primitive Geiger counters in the nose cones of these military machines. The rockets would soar above the protective blanket of Earth's atmosphere for just a few precious minutes. Our atmosphere, so vital for life, is an opaque wall to X-rays and gamma rays. To see the universe in these wavelengths, one must climb above it. In a brief flight in 1962, Giacconi's instrument detected the first X-ray source outside our solar system. An object in the constellation Scorpius X1 was blazing with X-ray light, outshining our own sun 1,000 times over in that band alone. X-ray astronomy was born, revealing a universe populated by black holes and neutron stars. It was a cosmos far more violent and dynamic than the one seen through optical telescopes. Later, the Vela satellites, launched to monitor for clandestine nuclear tests on Earth, began detecting something else: entirely powerful flashes of gamma rays from deep space. These gamma ray bursts, or GRBs, were a profound mystery for decades. They were like the FXTs of their day, enigmatic flashes with no known origin. It took years of painstaking follow-up observations to prove they were the birth cries of black holes forged in the heart of collapsing stars billions of light-years away. The discovery of GRBs taught us a crucial lesson. The universe is filled with transient events, powerful explosions that define the life and death of stars. And for every phenomenon we discover, countless others likely lie just beyond our detection threshold, waiting for technology to advance enough to spot them. The Einstein Probe, with its lobster eye vision, is the direct descendant of those early rocket experiments. It represents the culmination of our quest to build a persistent panoramic eye, one that can finally catch the faintest, fastest phantoms that have eluded us for so long. EP241107a was not just another data point, it was a test of this entire new philosophy of astronomy. The alert for EP241107a propagated through the Global Coordinates Network. This system is the nervous system of modern astrophysics, a rapid response network that connects telescopes of every kind across the planet. An astronomer in Chile might be woken by a text message. A robotic telescope in the Canary Islands might automatically slew its mirror, all without human intervention, guided by the machine-generated alert from space. The hunt became a multi-wavelength affair, a collaborative effort to build a complete picture. The first and most urgent task was to find a counterpart in visible light. The X-ray position from Einstein Probe was good, but not perfect. It defined a small patch of sky, a celestial search area, that could still contain thousands of distant galaxies. Large optical survey telescopes like the Zwicky Transient facility in California began rapidly imaging this region of the sky. Their software performed a complex digital subtraction. They compared the brand new images with archival photos of the same patch of sky taken weeks or months before. They were looking for a single new point of light, a star that wasn't there before. This is the afterglow, the fading ember of the initial explosion. Finding it is everything. An afterglow's light can be passed through a spectrograph, an instrument that acts like a prism, splitting the light into its constituent colors. Within that rainbow of light are dark lines, absorption features, imprinted by atoms in the host galaxy and the intergalactic gas the light has traversed. These lines are stretched or redshifted by the expansion of the universe. Measuring this redshift is the Holy Grail. It tells us the distance to the explosion. Without a distance, the energy of the event is unknown. It could be a small flare in our own galactic backyard, or a cosmic titan on the far side of the universe. As optical telescopes searched for the afterglow, another kind of eye turned toward the event. Great steel dishes arranged in vast, sprawling arrays across deserts and high plateaus. These are the world's radio telescope's instruments that listen for the universe's faint static. They are not looking for the initial flash of light, but for its aftermath. A colossal explosion, no matter its origin, creates an expanding fireball of debris. This shell of superheated plasma, a shock wave moving at near the speed of light, slams into the surrounding interstellar gas. This collision accelerates electrons, forcing them to spiral around magnetic field lines, a process that unleashes a torrent of long-wavelength radio waves. This radio afterglow can brighten over days or weeks long after the optical light has faded. It provides a completely different set of clues. The brightness of the radio signal tells astronomers about the total energy of the blast. How it changes over time reveals the density of the environment around the explosion. Was it in a dense, dusty, star-forming region, or in the clean, empty space between stars? Observatories like the Very Large Array in New Mexico, its 27 individual antennas moving in a slow, synchronized dance, began a patient vigil, listening for the faintest hum from EP241107a's location. Every piece of information, every photon captured from X-ray to optical to radio, was a clue in this grand cosmic detective story. The scientists were the investigators, and they were beginning to build a profile of their culprit. So what kind of cosmic perpetrator could create such a fleeting, powerful burst of X-rays? The list of suspects is short, and each one is more extraordinary than the last. These are not events involving ordinary stars, but the violent interactions of their dead remnants. The leading hypothesis, the prime suspect for an event like EP241107a, is one of the most extreme events the universe can produce, the merger of two neutron stars. A neutron star is the collapsed core of a massive star that has exploded as a supernova. It is an object of almost unbelievable density. Imagine taking a mountain, grinding it into a fine powder, and then compressing that powder until it fits into a single sugar cube. A neutron star packs the mass of our Sun and then some into a sphere just 20 kilometers across. Its gravitational field is so intense that atoms are crushed out of existence. Protons and electrons are forced to merge, leaving a pure ball of neutrons. Often these bizarre objects are born in binary pairs, locked in a gravitational waltz. For billions of years they can orbit each other in serene silence, but their dance is not eternal. According to Einstein's theory of general relativity, these orbiting, accelerating masses should constantly radiate energy away in the form of gravitational waves. These are ripples in the very fabric of space-time, invisible, silent waves of gravity. As the binary system loses energy, the two neutron stars slowly spiral closer and closer together. Their orbital period shrinks from hours to minutes to seconds. In the final moments, they are whirling around each other thousands of times per second, their colossal gravitational fields tearing at their surfaces, whipping them into distorted shapes. Then they collide. The impact is a cataclysm of unimaginable proportions. The collision unleashes a blast of gamma rays and creates a kilonova, an explosion 1,000 times brighter than a standard nova. In this inferno, the fundamental laws of physics are pushed to their limits. The neutron-rich debris from the collision undergoes a process called process nucleosynthesis. This is the universe's ultimate alchemy. Elements heavier than iron are forged in an instant: silver, iodine, platinum, uranium, and gold. Every wedding ring, every piece of gold jewelry on Earth contains atoms that were likely forged in the collision of two long-dead stars billions of years ago. The X-ray flash of EP241107a could be a key signature of such an event. It might be the light from a powerful jet of material punching its way out of the debris cloud, or it could be the emission from a newly formed hypermassive neutron star, or even a black hole settling down after the cosmic violence of its birth. The detection of such an event in X-rays, possibly alongside a gravitational wave signal from detectors like LIGO, would represent the pinnacle of multi-messenger astronomy, seeing and feeling the same cosmic event. But there are other suspects in this celestial lineup, other paths to a fast X-ray burst. Consider a different kind of deadly pairing, a neutron star orbiting a white dwarf. A white dwarf is the remnant of a sun-like star, a glowing ember the size of the Earth, but with the mass of the Sunday. While dense, it is nowhere